Okay, exponents. You guys have seen this before. You've seen these things before, right? All right, so basically, what an exponent really is, it's just a repeated, like an addition, right? So for example, if we had x3 to the power of 4, right? It's basically like doing 3 to the power of 4. So it's kind of like 3 times 3 times 3 times 3. Now what I'm doing is I'm putting this, it's basically 3 to the power 1 times, like, so it's 3 times 3 times 3 times 3 times 3. All right, so 3 to the power 4 is going to be, so 27 times 3 is 21, 81. Right? I think so. We do that in a calculator. Now, you could do it on your calculator to figure it out, like you can press 3 times 3 times 3 times 3 times 3. That's the annoying long way to do it, though. Right? So when we have a number, like 3 to the power 4, there are different parts. So this part here, the big number here, we often refer to this as the base. All right? This is referred to as the base number. That's our base number. And this little number, well, that's the exponent. And all that's doing is telling you how many times it's being multiplied by itself. So 3 to the power 4 is just 3 being multiplied by itself 4 times. Right, which I did in the example up there. So 3 times 3 times 3 times 3. And we get 81. Right, so if I'm doing other examples, so 2 to the power 5 is really just 2 times 2 times 2 times 2 times 2. Now that's confusing if you do it on your calculator, right? It's annoying, like, wait a minute, how many times did I just times by, I don't know. So you can get messed up. But in this case here, so 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Or we can do 5 to the power 3, which is just, again, 5 times 5 times 5. So the little number is just telling you how many times itself it is. So 5 times 5 is 25, times 5 is 125. What about this one? What's going on there? X to the power 4. That's weird. All that's happening here is just x. Now, when I have x's or I use letters, sometimes I'll use a little dot. In math, sometimes we do this little dot. And that just means multiply by. So it's just x times x times x times x, right? But in the end, it's just going to be, we always just simplify it, x to the power 4. Like, it's just the same thing. So this here is the same thing as x to the power 4, right? 125, we could rewrite this and say it's just 5 to the power 3. If we wanted to. If we memorize those different things, we could definitely do that. All right? Now, sometimes we're going to do something with an exponent that might have a negative number. So we have to be very careful because this value right here, negative 3 in brackets to the power 2, is not the same as this. Whoop, come on back, buddy. These two numbers are not the same. They don't equal each other. That's weird, right? You could try it on your calculator right now. You could say, all right, negative 3 in brackets. Why isn't that working? They don't give you the same answer. Because negative 3 in brackets squared is equal to basically this, negative 3 times negative 3. Right? In your calculator, it works like this. And a negative times a negative is going to be positive, so it just ends up being 9. So that one's 9. But if you go like this, what's happening is it goes like this. Your calculator does this. So this one equals negative 9. When the negative is out front of a number, if you don't put brackets around it, it will not multiply it by itself with the negative in front of it. It'll assume that the negative, it'll take it off of it. It detaches it. All right? Then it applies the negative on it again. So if you take negative 3 to the power 2, like this, without the brackets around the negative 3, it messes everything up. It messes your answer up on a calculator. That's the whole point of what I'm trying to say here. And it makes it remain negative. It stays negative, regardless of whatever the exponent is. Let's do a couple examples. Negative 4 to the power 4. It does not have the bracket around it, right? All that's happening really is like the negative's coming out front, and it's going to be like this, 4 times 4 times 4 times 4. 4 times 4 is 16, times 4 is 64, times 4 again is 256. By the way, I'm not a genius, I just do this a lot. So I remember some of these. In case you're wondering why I'm able to get them. I would normally not be able to get them. I would normally be doing this on a calculator. I'm not that smart. I just see them repeatedly. It's negative. Right? It's negative because the negative was not in the brackets with it. We'll try another one. This one is in the brackets. So negative 3 to the power 3 is negative 3 times negative 3 times negative 3. Anyone know what the answer is going to be for this one? Well, what's the number, first of all? The number is going to be the same no matter what. 3 times 3 is 9. 9 times 3 is 27. How many negatives do we have here? We have 3 of them, right? We have an odd amount. Anytime you're multiplying an odd amount of negatives, it's going to stay negative. If there were an even amount of negatives, this would be a positive number right now. Let's try this one here. Is this number going to be negative or positive? It's not in the brackets though, right? If it was like this, it would be positive. Because it would be like negative 5 times negative 5. But it's not in brackets. So what it's doing is putting the negative out front basically and going 5 times 5, which is negative 25. Whereas this one here is negative 5 times negative 5. And when you have two negatives multiplying each other, it's positive. So exponents can be tricky. We have to pay attention to them. When you're using a calculator, brackets matter. If you don't use brackets, or if you're kind of sloppy about your brackets, it will mess things up. What about with its fractions? What's that going to look like? Is it really complicated? Right? We have 2 over 5. What's actually happening here? It's just the repetition, like this. 2 over 5 times 2 over 5 times 2 over 5. And when we multiply fractions, basically just multiplying the top numbers all across. We're going straight across like the top numbers, and we're doing the bottom numbers too, like this. We're basically going like this. So 2 times 2, 4 times 2, 8, over 5 times 5, 25, times 5, 125. So that'd be our final answer. So that's all that's really happening there. So basically, we can make a rule for ourselves. So if we have, I'm going to use, sometimes we use, when we're trying to make a rule, we use letters. So if we had a over b to the power some number n, all we're doing is basically a to the power n over top of b to the power n. Right? So basically this applies to both. The n value is happening to both terms. All right. So try a couple on your own, and I'm going to see how you guys are doing. All right, I'll come around and see how you guys are doing. So try these 3 that you have on the paper in front of you. So on our first one, right, if you were to expand it all out, which some of you guys did, some of you kind of wrote it out like this. And some of you just wrote the answer, which I'm fine with as well, but just for the purpose of kind of writing it all out. You got 1 over 125. Right? I think everyone got that one. So everyone doing that. Okay, and same thing here. Basically all we have right here. Alex, you were doing, what did you get? What was your final answer on this one? 1631. Great. Right? So basically it's 2 to the power 4 over 3 to the power 4, which we end up getting 16 over 81. Now some of you have fancy calculators, so you can put the whole fraction in there, and even on your phone, if you do it properly, you can do it, like you can put this fraction in and just press the exponent. There is like a cool button that's a way of doing this on your calculator. That's a lot easier, right? Because if you had to put a fraction in and go 2 over 3 times 2 over 3 times 2 over, that would take a long time. So on your calculator, if you wanted to figure out a fast way of doing it, if you were to go like this, if you went like this, you press bracket and then you went 2, and there might be like a fraction button you have on your phone, and you go like this, and then sometimes there's a button that looks like this, x to the power y, or on your phone there's a button that kind of looks like this. Both of those things mean to the power of, right? So if you press any number and then you press this thing here, basically the number that you entered in takes the place of x. It means you put in the base number. And then the second number that you put in, after you press this button, means the power of what exponent. So you can try it on your phone right now. Like if you took your phone out and you went like 5 and you press this button and then you press 3, you should get 125. Right? Try that. Or, like I said, you could press, it might be this button, depending on your phone. If it's neither one of those, let me know. I'll try and point it out to you. But that's kind of the fast way of doing it. Did you try it? Got it? What does your button look like? Is it X?
It's still X form.
Okay, there you go. You want to try it, Zane? Give it a try? Yeah, try it on your phone. Right? You can do something ridiculous. Like you can go like 2 to the power of 8. What does that equal to? It's 2 to the power 8. 256? Can you do a fraction? That would be another question too. So let's see on your phone what you can do here. Press the second button. Where's the second? Yeah. Yeah, I don't know. I'm not sure how I would do it on your phone necessarily. So I don't know if I would be able to do the fractions on it. But anyway, some phones have one that's like this. It's like A over B or something like that. So basically letters are always the placeholder kind of thing. So sometimes on your phone you're able to put a fraction in and it can give you an answer in a fraction. But in any case, even if it didn't, right, you just do the top number, find the exponent for that one, and then you could do the bottom number after that. All right, last little bit. This one stars Chloe. I put Chloe in this one. All right, so let's imagine we're going to see an application of how exponents can be useful to help us explain things. So sometimes things happen in an exponential way, right? So for example, imagine Chloe started this terrible, terrible rumor, which is obviously would never be true, that Mr. Sean steals all his lessons from some teacher over at Easto. Never happens. Anyway, she starts by telling 3 people on the first day. And each one of those people tells another 3 people. And each of them tells 3 people the day after that. So on day number 1, right, the first person, so on the day number 1, Chloe tells 3 people. Right? It's just, so that's just equal to like 3. So that's like 3 to the power of 1. Right? Those are the 3 people. And after that, she'll make it wider. Right? And after that, those 3 people that Chloe originally told, they each tell 3 people as well. Right? So now new rumors is there's now 9 new rumors, right? Because we've added 3 more. So expanded form is just basically 3 times 3 to the power of 2. Shall write it like this: 3 to the power 1, 3 to the power 2. Right? And then the next day, those 3 people each tell 3 people. And then we have 27 new rumors. And so on and so forth, right? Another day goes by, and all those people start telling 3 people. So that's 3 to the power 4. That's 81. And then those people tell 3 more people. It's 3 to the power 5. Now you've lost me, because 3 to the power 5, 3 times 81, 284? I want to say. Maybe someone can figure out. What's 3 to the power 5? $243. Ah, that makes more sense. But then 3 people, each one of those 243 tells 3 people. and so on and so forth. And then we get to the point where after 18 days, how many people know? What's 3 to the power 18? That's a tough one. Some massive number, probably. Did you get a number?
It's like 300,800.
There's like 387 million.
Wow, that's a lot. Let's go like this. 420, 489. Okay. So assuming that each person tells 3 people, so after 18 days, basically beyond the entire population of the United States knows that I'm a stealer or I'm a thief, right? It doesn't take long. It really doesn't take long. That's a crazy amount of time. You can see how things compound. That's called compounding. When it builds up, it goes faster and faster and faster, right? And actually, that's what the whole idea of COVID is often about, right? You've heard of we're going into lockdown, we're coming out of lockdown. And sometimes people talk about something that's called the R rating. I'm not sure if you've heard this or not, but they're basically talking about how fast the disease is replicating itself. Now, if we keep the R rating, the replication level, under 1, that's what they mean is the exponent to how fast the disease grows is less than 1. If it's less than 1, the disease is generally not growing. It's actually retreating. It's getting smaller. But if it's greater than 1, that means we're gaining new COVID cases every single day, right? So right now it's right around neutral, which is good, but preferably we want the cases to drop. So we want the case number to be below 1, right? Now, before we went into lockdown, it was well above 1. And we can see how quickly it steamrolls, right? This is with the exponent, or we have a base number of 3. Now, with a disease, it tends to be this number would be 1.1 or 1.0 something or whatever. It's low, right? But then the R rating is the exponent factor. So how fast it quickly builds up. It doesn't take long before everything gets really out of control, right? So if we hadn't done anything about COVID, let's say we did nothing, everybody would have gotten it. Eventually everybody would have pretty much got COVID, right? And eventually it would have just gone off the charts, how many people got it. So most of us, again, would be fine. It would be, you get sick, but some people would get some bad things happening, and then a lot of older people would basically just die. So there's lots of different things that might have happened. But this is how quickly, so diseases, when we talk about diseases, not just filthy, dirty rumors about Mr. Shantz, but when we talk diseases, they expand, they grow exponentially. They definitely can. So especially if you let them grow by themselves, that's the way it goes. Same with bacteria. If you don't wash something, or you when you finish washing something, let's say you take put your dishes in the dishwasher and you take them out, they're pretty clean, right, to start off with, right? But if you leave them there for a little while, it starts off slow. But if you leave it there and it just builds and builds and builds, right? Does anyone have any moldy cheese in their house right now? I probably do, but anything moldy in your house? No? Ever gone to your locker and left some food in it after a little while? Come on, I know the guys have. You left a sandwich in your locker at some point. Have you?
I think I left the hot chocolate cup and Timmy's in there for 3 months after the first one.
Was it gross?
Yeah.
Oh yeah, right? Because the bacteria builds up in it and it gets disgusting, right? And so bacteria, that grows exponentially too. It starts off and it's probably fine. When they tell you if you buy something from the store or you get some fast food or something like that, it's okay for 4 days. The reason why they're telling you it's okay for 4 days is because the bacteria under that 4-day time window hasn't grown very fast. It doesn't tend to grow particularly well in cold temperatures, which is why we store stuff into the fridge for 4 days. But with that same thing, anyone here drink milk? A lot of you guys don't drink milk anymore. Dairy milk and milk bags and that kind of thing. It's got an expiry date on it, right? So that expiry date is like a bet. It's basically a bet saying, we don't think that the bacteria will have enough time to grow to the point where it could actually poison you or do something bad to you before this date, right? And then after that date, Who knows? Maybe the bacteria is growing fast. They actually don't even know. They're guessing, right? They're trying. Obviously, if you were the one making that choice with a best before date, you would probably err a little bit on the side of caution. You'd probably be like, let's make it so we're not going to push it, because they could get sick if it's like a 1 minute after. They don't really know exactly the day, right? But basically, they're betting the growth of bacteria in milk or cheese or whatever. That's what a best before date is a prediction of when that bacteria will get to the point where it probably would make you sick. But they're always like trying to be on the safe side, right? Anyone here ever drank expired milk before? Yeah, Abby's like, yeah, whatever. Do you care how long it's been expired? When do you draw the line?
I don't think I've ever it wasn't expired, it was just bad when we bought it.
Oh, right, okay.
Yeah.
So sometimes that happens, right? Sometimes bacteria would go on it. They could grow faster than that. What about you, Dalton? Did you ever drink expired milk? Yeah, you have? Where do you draw the line? How old is too old past the date? A month of milk? Wow, that's pretty risky. What about yourself? Milk, or what do you drink, or what did you have that was expired? Milk, yeah. How far is too far? A week, you think? Yeah, I think I've probably done 2 weeks, maybe 3. And I'm always, when you're drinking, you're kind of like, is it okay? You're like, am I getting sick here? Am I going to throw up like an hour? Because I have definitely had milk or something like that. I think maybe it was cheese that I was kind of like, shouldn't have done that. Nope. And then you feel sick later on, pretty quickly afterwards, actually. So your body kind of knows that kind of thing. So we can model those things using exponents, and that's what actually we're going to do during our course this year. Is we're going to look at applications of exponents and exponential functions. So things that either grow or change on an exponential rate. So it could be growing, but you could also decay an exponential rate, right? So let's say that Zane has a secret stash of plutonium in his basement or something like that, right? And it's slowly decaying too. So it's actually and that happens as well. Or certain things that can have a radiation decay or changing to lead over time, right? Like uranium will change to from uranium to other substances like lead. So they have a half-life and that kind of thing. So when something has a half-life, it's basically talking an exponential rate, but on a decay as opposed to a growing rate. So I won't be able to get to uranium for you guys this term, unfortunately, but maybe we'll just play with our fake uranium, unless Zane can bring some from his stash, which please don't do that. Okay, so we could do lots of multiplication, but we can always use a calculator, which is what we tend to use.